Okay, so today we're going to finish off the last type of problem that we are going to see in projectile motion, that being an asymmetrical problem. Again, asymmetrical just means that it is not symmetrical. It is not going to return back to the same height at which it has started. Okay, and here's the good news. All of the things that we've done in this problem, we've done before. Like we just did in the previous projectile motion problems, we're just going to pull it all together. Okay, so here's the problem. A stone thrown from the top of a 45-meter high building is given an initial velocity of 20 meters per second at an angle of 30 degrees. We have four things in which we are going to determine. Okay, let's start with our data tables. Vivash, give me something that we know we can put into our data table. Good. We have negative 9.8 for G. And I'm going to say that that's probably going to be, for right now, where we're going to stop. Negative 9.8. Now, we have an initial velocity that's expressed in 2 dimensions. So who wants to take a wild guess what we have to do before we do any of this? We have to find the x and y components. Excellent, Carly. So let's do that. Okay, we'll write them out here. So Vx is still going to be V cosine theta. Okay, and Vyi is still going to be V sine theta. We know the initial velocity itself is 20 meters per second, so 20 times the cosine of 30 degrees. And this would be 20 times the sine of 30 degrees. I know that becomes a little easier when we know our unit circle, but even if we don't know our unit circle, that's still okay. And Carly, since you were a big help earlier, what do we get for Vx? 17.32321 meters per second, absolutely. And Vyi? Good, 10 meters per second. So we can put that into our data table. I would suggest it. So Vx is going to be our 17.321. Vyi would be 10. Okay. Now I know we might have a tendency to want to start to put other things together. Let's not do that yet. Does everyone have this step written down, our components? Okay, I'm going to erase it just so I have plenty of space. Obviously for you, you have a full page to go ahead and put everything that's there. I just have a little bit less space than you. So let's go ahead and let's take a look at the first part of what we need to solve for. So Michaela, please do me a favor, go ahead and read what part A is asking us to solve for.
The time at which the stone reaches its maximum.
Okay, so the time that the stone reaches maximum height. Believe it or not, when we had an asymmetrical free fall problem, we're going to do the exact same thing as to what we did then. This is not going to be the quadratic as we've used it. This is not going to be the t equals square root equation. Absolutely. So to find the time, that I'll just call this time up. That way we kind of know that it's just different than the total time. We are going to use the V final minus V initial all over G. Now, Alex, because we were just talking about this earlier in class, we're going up to maximum height. So what do we have to do in this situation? This is where we treat our V final as 0. I would like for us to get into the habit that this is the only time that we use V final as 0, when we're doing something related to maximum height. Okay, so what are we going to use for V initial? Okay, we need to use our Vyi. So that would be all over 10, or sorry, 0 minus 10, all over the negative 9.8. I know I'm going to kind of draw on top of our diagram here. But let's go ahead and solve for that. I think we should know, based on mental math, we should get a value slightly larger than 1. And Alicia, when you feel like you have your response, let us know. 1.020 seconds. Okay, would be the correct response for part A of this. Is that going to go into our data table? No, I wouldn't. because this is not the total time. We're just asked for the time up to the maximum height. Which is kind of why I also put the subscript up in there to kind of be a friendly reminder to us this is not everything that we need. When we are asked to solve for the total time in the next step, we should just double it, right? No, this is an asymmetrical problem. We know that we have a different process when we get to step C. Okay? Are we ready to go on to part B? Okay. Is that a complicated step? I don't think so. But again, with a new process, we just make sure that we understand that's what we need to do. So now we're going to figure out the stone's maximum height, where we're going to go ahead and solve for it by means of delta y. Specifically, just like in the free fall problems we did, okay, VF squared minus VI squared all over what? 2G. Alex, remind me again, what are we going to use for a V final since we're asked to figure out what the maximum height is? Good. Okay, so it would be 0 squared minus 10 squared, because we're still using our vertical data, all over 2 times negative 9.8. Close, close, pluggy chuggy. And Jacob, when you have a quality response?
5.102 meters.
Okay, 5.102 meters. Now, because we are well versed in solving asymmetrical free fall problems, which are just along the vertical axis, we know that we're not done. Jacob's going to already get it because he is the man. What do we have to do?
Add the height of
In this case, we have to add the height of the building, which is
45 meters.
45 meters. Don't you dare touch your calculator. What do we get?
50.102 meters.
Good. We add the 45. We get the 50.102 meters. Okay, and that would be our height relative to the lowest possible point. Now, I also need to remind you, this is a problem where we start high and we finish low. We haven't really done a whole lot of this, but it is entirely possible for us to start low and finish high. Okay? Instead of projecting an object off the roof, we could be standing on the ground, throw an object up that ends up landing on the roof. Okay? We're going to solve that just a little bit differently in this step, but it's still the same process. Any questions on A or B so far? Have we done this before? Absolutely, and I hope that this is looking familiar for us. Unfortunately, again, I need to do some erasing. Does everyone have this? Okay. All right, so then in part C, Justin Hampton, why don't you go ahead and read us what we have for part C. Okay, we need to find the total time of flight. Okay, so how do we think we're going to solve for this step? What process are we going to use to figure out total time? The same thing as what we did in asymmetrical free fall? Start with the cube. We're going to have to do the quadratic here. Okay, so if we set it up, 0 equals the 1/2 gt squared plus vit minus delta y. Okay, so that is our quadratic rearranged to do what we need to do. For all of these problems, the 1/2 g part of it should be pretty easy. What do we put in there, Michael Taylor, for that? Good, negative 4.9 t squared. Nick, what do we do with the VIT? What VI do we use?
10.
Good. We have to continue to use our vertical data. So plus 10t. Now here's the thing. To be consistent with this, we use our launch velocity, which starts here at roof height. Okay? So if we're going to go from there all the way back down to here, where our projectile is going to land, this is where we need to be careful. What is the displacement from start to finish? The Does everyone see why it's negative 45 and not negative 50.102? Okay, because of where we start, but here's where we be careful. So it'd be subtracting a negative 45. So in terms of the quadratic, we put that as plus 45. Now, I'm not going to go through this on the board, but this is where we go ahead. Make sure that we have our window set properly for our calculators. I know we did clear since our last test. So the minimum of negative 100, maximum of 100, scale of 10 on both the x and y axis. Let's go ahead and graph this and find the 0. Go ahead and calculate the 0. Anuj, you got it?
Yeah.
What do we get?
4.218 seconds.
Thank you. Okay. Is that what everyone gets?
Yeah.
Okay. Does it seem reasonable? I mean, if we kind of go back to our original data, it was about 1 second on the way up. Okay. It ends up being about from maximum height all the way down to the ground would be about 3 seconds. I mean, it's reasonable. Okay, giving us the total of 4.218 seconds. Okay. We would be concerned, obviously, if we got less than a second, and there'd be something going on in terms of our calculation. So that's good. All right, last one. Okay. Now understand that this is bolded and underlined for a reason. Okay. We haven't done it together as a group, but I just want to make sure at some point we've discussed how to do it. More often than not, you will be asked for the final speed. But in this case, we are asked for the final velocity. So we have a couple of steps. All right. What do you think is the first thing that we need to find if we're going to try to find the final velocity? I'll give you a hint. It's actually one of the things that we have to solve for something that's launched horizontally. We already have time. Do we need that? Because think about this. When this goes ahead, it's projected here, comes all the way up, comes back and strikes the ground somewhere over here. Let me move that. Isn't this also striking the ground in 2 dimensions? Aren't we going to need to do what we did on those problems, which is create the right triangle, find those 2 components. Actually, I did a bad job drawing that. It should be this way. But anyway. So we need to find Vy final. Plus or minus square root of Vy initial squared plus 2g delta y. Close it off. What should we use for Vy initial? We should use 10 squared plus 2 times negative 9.8 times negative 45. Close that off properly, then we'll go ahead and solve for that. Why are we using the negative 45? Because if we're using the launch velocity component of positive 10, that's our starting point in terms of our data. Where's our finish point in part of our data? At the ground level. That's why we need to go ahead and use the negative 45. Aaron, when you get a chance, let us know.
I got 31.337.
Okay, technically it should be negative. I know with this one we have the plus or minus. I know in the next step of what we're going to do, it's going to take care of the negative anyway. But do we all get 31.337? Okay, good. So now step number 2. Let's find the V final. Why do we need to find V final? Because it is the hypotenuse of the right triangle made by the 2 components. So we're doing Pythagorean's theorem, but in physics speak, that's going to be Vx squared plus Vy final squared. Take the square root of the entire quantity. So now that we have that information, okay, the square root of, what do we have as that component? 17.321 squared plus 31.337 squared. And please put it in as 31.337 squared. I know it is negative, but when we square it, we'll take care of that. While you're doing that, I'm going to do a little corrective work over here. Elson, what do we got? 35.805 meters per second. Show of hands, how many agree? Good. Anybody disagree with it? Question? Why isn't it negative? It's a great question. Understand that this is a two-dimensional velocity. It's the hypotenuse of a right triangle. Would you ever express the hypotenuse of a right triangle as negative? For the same reason why this is not negative here. We do not assess a direction, because for us right now the positive and negative would just assess a direction. You don't assess that based off of a two-dimensional thing. That's why we'll handle the velocity piece of it in just a second. Okay? So what have we solved for? We've solved for the final speed. So if the question had just asked us for the final speed, at this point we're done. Question?
I was wondering why negative 31.337 was the answer. Why get to go an extra step?
Okay, that's a good question. Because Vy final, what we solved for, remember how earlier we kind of went back to some of the stuff we did and we were talking about, hey, we break it down in terms of the two-dimensional components. This is just the vertical component of it falling. It doesn't take into account, it's also moving horizontally at the same time.
Okay.
So that's why it's not a complete answer. Sure, if we somehow could blindfold ourselves and only see this entire event vertically, it would be a free fall problem and then we'd be done at that point. But because it is a two-dimensional problem, the final velocity is two-dimensional. But we're solving for the components of that final velocity. So that's why we have this extra step of Pythagorean's theorem. Just like for a projectile launched horizontally, the final speed of that one is also a two-step process. Now, I'm going to say this, 90% of the time, I'm going to ask you for final speed. But just because I feel like that this is an opportunity for us to do this together, I want to walk us through what do we need to do if we need to find the velocity. Back to our truest sense of what is velocity, we need to find that. We have to find theta, the angle that this is with respect to the x-axis. How do we do that? The inverse tangent. Now let's take a look at this right triangle. This is the angle we're trying to find here. What is the opposite side? Vy final over the adjacent side of Vx. So the inverse tangent of Vy final, which we found up here as the 31.337 over our Vx, which was our 17.321. Let's take a minute with that. Anuj, you seem like you're sitting with an answer, ready to go.
61.069 degrees.
Okay, that is what we should calculate for that. So if we had to put it all together as a final velocity, it really should be 35.805 meters per second at 61.069 degrees. And how would we describe that? Would that be above, below, below? It's going to the right, so below positive x-axis. And technically, all of that would be our final answer. Now again, 90% of the time, you're going to be asked for final speed. You will not have to go ahead and calculate theta, and you won't have your really long final velocity answer. Yes, ma'am?
What are the symmetrical ones would it ask us for velocity?
Symmetrical is actually very easy. And if it's okay, let me put up another slide and let me answer that question. Well, let me do that in a second because I want to make sure we're finished here. Really good question that I want to answer. Anything based off sample problem C? Questions we have? Okay. Let's do this. Blank page after. So let's say we have a symmetrical problem, and let's get to Alessia's question. So let's say, and I'm just going to make up some numbers. Let's say we have an initial launch velocity of 20 meters per second at, I don't know, let's say 45 degrees. By the nature of the fact that this is a symmetrical problem, what should the final velocity be? Shouldn't it be 20 meters per second at, that's a bad at symbol, at 45 degrees? Now we would change the above or below because it is a velocity. And again, the negative is only assessing along one axis. It's two-dimensional. So if we're truly asked for what is the final velocity, it's symmetrical. Whatever the launch is, it's going to have a symmetrical piece on the other side. But the only thing that would change is instead of it going in a positive y direction, you're going in a negative y direction along that axis. So we would just say, let's say this would be above the positive x-axis. Wouldn't this just be below positive x-axis?
So because we say
The directional piece changes because up here and then down here, but that's it.
we don't put negative because we said at 45 degrees below.
Negative can only be assessed along one axis. If we have two-dimensional motion, you cannot assess a two-dimensional speed or velocity as either positive or negative. We can assess the angle with respect to a positive or negative x-axis, but we can't just leave the direction simply as positive or negative because it's two-dimensional. So, does that kind of answer the question? It's actually easy because it's the same thing. We just change effectively where the angle is measured from. Really good question.